Okay, suppose we have a speech spectrum that looks like this, and we want to resynthesize it. We want to create a model that will allow us to resynthesize that spectrum from a simplified parametric model. Well, you've already seen that S of e to the j omega is equal to h of e to the j omega times the excitation, e of e to the j omega, where h of e to the j omega is a representation of the filtering caused by the resonant characteristics of your vocal tract from your glottis to your lips. And so it's some kind of smooth spectrum that looks like this. The excitation can be either a voiced excitation, which is a set of window functions, each modulated up to a harmonic of the pitch frequency like this. Or it can be an unvoiced excitation, which is a random noise spectrum. And here's a particular instance of the magnitude of a complex Gaussian random noise spectrum. Looks something like this. And, well, the problem with this model is that this pitch spectrum, these voiced harmonics, are very simplified. So here's an image from the Font, Liliencrantz, and Lin paper that started us with the voiced model in the first place. They said that the glottal excitation, the air pressure just above the glottis, isn't actually an impulse, right? It's this thing on the upper right. It rises as the flow is increasing, and then it suddenly drops to a negative spike as the flow is decreasing. And that thing doesn't have a perfectly flat spectrum. In fact, that thing has kind of a low-pass spectrum, as shown in the figure at the bottom. So the figure at the bottom shows a whole bunch of different spectra for different parameters of this glottal excitation model, but the one that's most typical is the bottom spectrum, where you see harmonics of the pitch frequency, but those harmonics are largest at low frequencies, and they become much, much smaller in amplitude as you go to higher frequencies. And we see the effect of this in real speech spectra. So if we go back up to the spectrum at the top, you'll see that the low frequencies are clearly voiced. The first 13 harmonics of the fundamental are very clearly visible. But up at high frequencies, the voiced excitation has actually dropped below the unvoiced excitation. The reason for that is that even when the glottis is opening and closing periodically, there's still some turbulence being generated at the glottis. And at very high frequencies, the voiced excitation is so weak that the unvoiced excitation dominates. And it's not even so simple as that. You can see that there's this low-frequency voiced band and this high-frequency unvoiced band, but right here there's 3 harmonics that are very clearly voiced. And then just below those, there's this section of about 2 harmonics that look like they're primarily unvoiced. This phenomenon was modeled for synthesis in a paper called Multiband Excitation Vocoding. This paper was written by Griffin and Lim in 1988. All of the figures that I've shown on this page, except for the Font and Liliencrantz and Lin paper figure, all of the others are from this paper, and they show how we can solve this problem for practical, good-sounding speech synthesis. So their model says, let's start with a speech spectrum. Here's the input speech spectrum, and we want to try to regenerate that speech spectrum from a parametric model. What they said is, let's just model the speech as being partly voiced and partly unvoiced. So it's voiced in the bands where this VUV function is 1, and it's unvoiced in the bands where the VUV function is 0. And so if we take the voiced spectrum, the voiced excitation, and multiply it by the VUV function, and we take the unvoiced excitation spectrum and just multiply it by 1 minus the VUV function, we get a total excitation spectrum that looks like this. It's voiced for the first 13 harmonics or so, and then there's a period of about 3 harmonics where it's unvoiced, and then there's a period of 3 harmonics where it's voiced, and then it's unvoiced again at high frequencies. If we multiply that by the transfer function, we get a total speech spectrum that looks something like this, which is much closer to the original than we would get if we chose the entire band to be voiced or the entire band to be unvoiced. All right, to use this in practice, you need a little bit more information about how to actually do the synthesis. So let me focus on this in 2 parts. First, let me focus on the unvoiced parts, U of n. And the model for generating this will generate it in the DFT domain. We'll generate the Fourier transform of the unvoiced speech, and then we'll inverse DFT it. The Fourier transform will actually be generated using a random number generator. It's a set of Gaussian random variables. And those Gaussian random variables will have energies that are estimated from the original speech spectrum. So the energy of each FFT bin will actually be a parameter that's estimated from the speech spectrum that we're trying to model. All right, so the U of n, the F frame of the unvoiced speech, will be generated from the F frame DFT, which is a random variable. And so if we have U sub f of k that we've generated by some model, then we get U sub f of n using the standard inverse DFT formula. U sub f of k, on the other hand, will be 0 in bands that are voiced. And in unvoiced bands, it will be some kind of random variable. And now let me talk a little bit about what kind of random variable it is. So here's a picture of the VUV function. In the bands where this is 1, the U sub f of k is 0. In the bands where this is 0, U sub f of k is some kind of random variable. And the way that Griffin and Lim defined these bands was in terms of the excitation function. If you know the fundamental frequency, then you can generate a series of impulse trains that looks kind of like this. So omega naught is 2 pi over capital P, where capital P is some estimate of the fundamental period of the voiced signal. And the voiced excitation is 2 pi over capital P times the sum of delta functions, or actually more properly of shifted window functions. Right? And so they said, let's divide it into one band for every pitch harmonic. So the lower edge of the nth band is m minus a half times omega naught. The upper edge of the nth band is m plus a half times omega naught. And then in order to calculate the variance of the nth band, we're just going to take the input speech spectrum and we're going to average the energy in that band. So we're going to take the magnitude squared of the input speech spectrum and just average it from A sub m to B sub m. In practice, of course, this isn't done with an integral. This is done by adding up bins in the discrete Fourier transform. And so we get a model that looks like this. The unvoiced speech spectrum is 0 in bands that are voiced. And it's a Gaussian random variable, a complex Gaussian random variable. It has a Gaussian real part with a variance of 1/2 sigma squared, and a Gaussian imaginary part with a variance of 1/2 sigma squared in bands that are unvoiced. Once we've got the spectrum, then we generate the time domain signal by calculating its inverse Fourier transform. And then we have to go from these frames of speech, somehow we have to generate the continuous speech signal that we'll use for synthesis. And we do that using an algorithm called overlap add synthesis. And I'm not going to go into more detail here, but let me talk about linear interpolation between frames. So for example, for the samples U of n that are in the F frame, that is, they're between the timestamp F times capital K up to the timestamp F plus 1 times capital K, we just linearly interpolate. We start out with the unvoiced sample from the F frame, and as we go from that period, from Fk to F plus 1k, we gradually decrease the weight on the sample from the F frame, and we gradually increase the weight on the sample from the F plus first frame. So this is just linear interpolation. You could equally well do Han interpolation or Hamming interpolation or any other kind of, or sync interpolation, any other kind of overlap add synthesis that you like. Critically here, it doesn't need to be the same kind of frame, the same kind of window that you used for analysis in the first place. It's perfectly okay to do your analysis of the original spectrum using a Hamming window, and then do overlap add synthesis using a triangular window, as shown here, using linear interpolation. All right, that's the unvoiced part. Now let's look at voiced excitation. And here's a surprise. Overlap add synthesis of the voiced excitation signal fails badly. The overlap add synthesis that worked so well for unvoiced excitation fails for voiced excitation because the pitch period changes discontinuously at every frame boundary. And so here's a picture of what that looks like in the time frequency domain. This is a spectrogram, which is a plot of the energy as a function of time and frequency. And it shows that the harmonics of the pitch change suddenly at every frame boundary. So every time you go from the fth frame from the 0th frame to the first frame, suddenly all of the pitch frequencies change, and so you get this discontinuous jump, and that sounds really bad, as you can imagine. If you're saying ah, and then suddenly you jump to ah, it sounds really unnatural. And the problem, of course, is that the pitch period in frame f is usually not the same as the pitch period in frame f plus 1. And so if we estimate the fundamental frequency as 2 pi over the pitch period for all of the samples that are in the fth frame, that fails. So the solution we're going to use is to actually generate the voice signal in the time domain originally. We're not even going to generate its Fourier transform samples. Instead, we're going to generate the voice signal using a Fourier series. We're going to take the amplitudes, a sub m, and we're going to multiply them by the real part of e to the j m omega naught n. And that real part is just the cosine of theta sub m of n. And now here's the trick. Theta sub m of n, that's the angle. That's just theta sub m of n minus 1 at the previous sample, plus m times omega naught. Remember, omega naught is the number of radians per sample that it should change. And so m times omega naught is the number of radians per sample that the mth harmonic should change. And so it changes by that many radians from sample n minus 1 to sample n. And now if we use that kind of model where theta m is generated from m times omega naught, then we can plug in any pitch frequency we want. So for example, we can plug in a pitch frequency which is linearly interpolated from the fth frame to the f plus first frame, right? In the fth frame, it's 2 pi over pf. In the f plus first frame, it's 2 pi over pf plus 1, and we'll just linearly interpolate between those two pitch frequencies. So here's an image of the spectrogram with these nice linearly interpolated pitch frequencies, and you can see that there are no more any discontinuities. And so this sounds actually surprisingly natural, even though you can see that it's still stylized. It's still a linear pitch frequency, piecewise linear rather than piecewise constant. But piecewise linear is enough to eliminate the discontinuities in the time domain. And so suddenly it sounds much more natural. The amplitudes of the harmonics should also be continuous, and it usually works well enough to make them continuous using linear interpolation. You can also use Han interpolation or sync interpolation if you like, but linear interpolation, as shown here, usually works well enough. The only trick is that, of course, if band M is unvoiced in frame F, then you need to set the amplitude, A sub MF, equal to 0 in that frame. So we don't take the amplitudes directly from the original signal, we set them to 0 when that band is unvoiced.